If you are looking to learn geospatial Python, then you have come to the right place because in this tutorial, we are going to take a deep dive into Geopandas, which is one of the most foundational libraries for working with geospatial data in Python. During this tutorial, you will understand the core fundamentals of Geopandas, going through several different exercises and culminating in a complete project that you can actually work through and share as a portfolio piece at the end of the tutorial. We'll also cover several different other libraries that work nicely alongside Geopandas to help you extend the core capabilities of the library. Now, along with this video, you can actually get a certification for watching the video and completing a short quiz that proves that you actually completed the exercises over at my online course website, moderngis.xyz. All you have to do is head over to the website, moderngis.xyz, go ahead and find the Geopandas course, sign up for your free account, and get started. You can get access to the course materials there as well. This includes the Jupyter notebooks and associated data sets. And once you complete the final quiz, you'll get a certification that you completed the course, which you can share on LinkedIn or on your resume. Now, if you want to continue your geospatial learning journey after completing this course, you'll actually get a coupon to try out some of my other courses on my website. So with that, let's go ahead and jump in. So let's talk briefly about what GeoPandas is and how you can actually use it. Now, GeoPandas is built on or extends the Pandas library, which is a library that allows you to work with primarily tabular data and read into what is known as a data frame structure in Python. The easiest way to think about this is it's kind of like working with a table, and Pandas allows you to access functions to read in different data sources, things like CSVs. The easiest way to think about this is it's sort of like a table or even like an Excel spreadsheet. And the Pandas library gives you functions to not only read data in from formats like Excel, CSV, JSON, and many others, as well as functions to actually manipulate and work with that data. And then finally take that data out and export it in a format that you need. GeoPandas extends the Pandas functionality to add in the geometric or geometry data type to the Pandas ecosystem. So all of the things that you've learned in Pandas to work with and manipulate data apply to GeoPandas as well, because that's the core of that library. As you can see here, this effectively kind of shows you what this looks like. Now, just as I described, this is the GeoPandas documentation. You can actually see here, this sort of shows you exactly what this looks like. You have your data here in yellow, which is basically a Pandas data frame. And you have your geometry here, which is going to be known as a geoseries. Now, we'll discuss the difference between a data frame and a series later in this section. But for now, this effectively shows you what your data structure will look like in addition to your index over here. Now, in that geometry, that stores different spatial attributes like the projection system or the CRS, coordinate reference system, as well as some other metadata information about that geometric object. Now, of course, many times, of course, your data is going to be different than a CSV or JSON. You may be working with a GeoJSON, Shapefile, GeoParquet, or any other number of file types. And of course, GeoPandas allows you different functionality to read as well as write those geospatial files from this library. As you can see here, here's an example of this data. There's actually a example data set that you can go ahead and grab here to pull in this data set, which is the New York City boroughs. And you can see here that you have your 5 different boroughs of New York City, as well as the geometry or the multi-polygon that you can see here. Now, of course, you can write data back to that and also work with that geometry object to do many different things within the geometry itself, such as finding the centroid or finding the area. You can also work with 2 different data sets to do things like spatial joins or overlaps and different geometric operations like that. Now, I do recommend spending some time going through the GeoPandas documentation. They have really good documentation from this introductory section here. There's also a really nice examples gallery. So if there's something that you're specifically looking to do, I would take a look at these examples to see if there's something you're looking to work on and actually see what you can do here. So there's lots of different options for just lots of different options that go into greater detail than we have time to cover in this tutorial. So you can actually check these out and see what all of those look like. In addition, the complete documentation is listed here. If you go to the documentation header up here, there's some information on the user guide here that go into very specific operations, such as reading and writing files, if you wanted some more detail on that, as well as some of the advanced guides if you have some more advanced things. But here's where you will spend a lot of time, which is this API reference. So this will tell you all the different things you can do, such as operations on the GeoSeries. Like I mentioned, you can get the area or the bounds or the length of that different GeoSeries object. We can also take a look at what you can do with the GeoDataFrame and some of the different pieces here. Here's the reading in and out, or the IO operations for reading files, and then some of the different tools and spatial indices and things like that. So there's a few other pieces here that you can actually check out, but I do recommend, familiarizing yourself with how to read the documentation. I'll be referring to it a few different times during the course here, so we actually take a look at here's the operation we're doing and how can we use that. So I do recommend spending some time just kind of understanding what the documentation looks like and what you can expect. Now, to go ahead and kick off the actual tutorial, of course, you will need Python installed on your computer or a notebook service where you can actually install and run GeoPandas. I highly recommend using a notebook service such as Jupyter Notebook or a hosted Jupyter Notebook service. This will make life a lot easier, and all of the examples are in notebooks as well. All the notebooks you can use in a tool like Google Collaboratory if you want to use, but in this example, I'll show you how I set up Python on my computer to keep it as simple as possible to run different operations that I need. So if you have not installed Python, you will have to go and do that. There's a number of different ways to do that, and I'll include a link to a video that shows you some of these different steps and operations. You can actually go here to downloads and download this as well. This will get you the actual Python code that you can run and install it that way. You can also do it a couple different ways if you want to do that on Windows. I currently run on a Mac, so I use a program called Homebrew. So Homebrew will allow you to basically, so I like these tutorials from geeksforgeeks.org. They cover the different operating systems that you can actually install that on. So if you want to install Python, of course, with Windows, it'll walk you through the download steps here. You can actually download that, set that up, and go this way. There's also steps for Linux or Mac. So like I mentioned, you can use Homebrew. This is currently the way that I use it on my machine because it also manages the versions and things like that. So there's some different advantages there. I think there's a similar process in Linux, just using the core install tool there. You can go ahead and do that. So that's one thing that you can do. Now, what this will accomplish is install a specific version of Python on your computer. You may have a version of Python as well, so that's something to be aware of, but we'll talk about the difference between a global environment and a virtual environment, which is what we'll be using during this series of this course. Now, the tool that I use to run my notebooks is actually Visual Studio. Visual Studio is a very comprehensive development environment, or an IDE, that makes it very easy to work with a lot of different things, with no matter what language you're programming in. But it has really great support not only for Jupyter notebooks, but also for setting up and running virtual environments in a very seamless setting. So I recommend also getting a copy of Visual Studio. You can go ahead and download that. It's a completely free program, so you can actually download here. Sorry, Visual Studio Code, I should say. So you want to download that and set that up on your computer. So next we'll jump over there and actually get everything up and running. Okay, so before you jump into this step, you can actually go ahead and download all of the files from the course website over at moderngis.xyz. This will have all of the files and data set that you need. So once you do that, you just want to put those in a specific folder that you want. I've just set up a folder called Geopandas in my computer here, and this is where I'm storing all my data. So what you'll notice here is that I actually have this virtual environment already set up on my computer, just because I was building a tutorial and actually used this virtual environment. So I'm actually going to go ahead and delete this so you can see what it looks like running from complete scratch if you haven't set this up before. So we'll get rid of the virtual environment, and I'm going to remove this terminal window down here. So the first thing I want to do is actually open up another terminal window. And you'll see here that I have that. So actually want to kill that terminal there and open up a new one. So what I'll go ahead and do is just deactivate this virtual environment for now. So I'm just going to write deactivate and then clear out my terminal for the time being. Now, I have several different versions of Python installed on my machine. So there's a few different ways you can check to see which one is installed, and we'll need this for the next step to choose which version we want to use in our virtual environment so we can pick the right one for us. So to see which version of Python I'm running, I do know I'm running the version 3. So if I can type Python 3.version, I can go ahead and see that I have Python 3.9.6 running. And you can also do this. You can echo which Python you're running. As you can see here, I'm using Python 3, which is how I'm going to need to run those commands if I'm using my global environment. So if I want to try that again, you can see here that this is where that Python version is located. Now, I have other versions installed. I homebrew and things like that. I just use this one for some older libraries and things like that. But the good news is that Visual Studio will pick that up and help you get the right one in place. Now, normally when you're setting up a virtual environment, you have to run several commands and things like that. What's nice about this is that it can kind of do all of that visually. So what we want to do is go up here, and you kind of want to use this forward pointing symbol, I believe is what it's called. But basically this arrow here. And I want to look for Python and create environment. So this is what I'm going to click in here. So it allows you to create two different virtual environments. You want to pick this one here, which is the VENV, or virtual environment. You can do that with Conda as well. I just prefer the virtual environment. I think the syntax is just a little bit easier. And now you can see I have two different versions here. There's that version 0.6, which we saw earlier, and I have the version 12.6, which is a little closer to the most current release of Python that's out there. You can see it just runs and installs in different locations. So this is the one that I'm going to use here. So I can pull that in. And what's going to happen is it's going to create my new virtual environment. So it has all of that set up here. Now, like I said, normally you'd have to run the commands to do this. All I have to do is point and click to do that. Now, if I close out this terminal, I can open that back up, and then I can actually start to use that new virtual environment. So when I open up my new terminal, now you see it actually shows that it's using that virtual environment here. So if I run these commands, it will start to look a little bit different. So if I write which Python, you'll see here that it tells me, okay, it's in Geopandas and it's using the virtual environment version of that. I can check which version. You can see here it's 3.12.6, which is exactly what we wanted. So this is allowing me to set that up. And from here, I can start to install and run and use libraries. I can do that through here, or I can do that through the notebook interface, which we'll see in a minute. But if you choose to do it this way, you're going to use a library called pip. It's connects to PyPy, which is a service that allows you to actually access and work with different libraries. So what we can do here is we can look up the listing for Geopandas. And you can see here at here's the actual version. It has a release history and things like that. And it gives you the installation code. So it's just pip install Geopandas. So we'll go ahead and run that here. And you'll see it's going to run all of the commands to get everything set up in my virtual environment. Since I deleted my old virtual environment, everything is going to be fresh and new in this one. So you can kind of keep this in place and use it over and over if you want to, and it'll keep all your libraries stored. This works for me a little bit better than doing this all globally, because you have it stored on your computer and you get different mismatches, as you saw earlier. So this keeps it very clean and contained to run it all in that virtual environment. So now that we're set up, what we want to do is open our first notebook here. So this is our first notebook that we'll be running. What I'm going to do is first, I'm going to clear out all the outputs, so we won't be seeing everything that we need to do. Now, a few different things is that you'll notice within this notebook environment, if you have not worked with it before, each of these is a different cell that will be running here. So you can see all the different things here. You can run that by pressing basically the run all if you want to run every single thing. There should be a shortcut. If you've never set this up before, it uses like Shift Enter, and that will run a cell. And then you can also see which version it's running and where it's running from. So you can see it's using the local version of Python here. I want to actually use that virtual environment that we've set up and run everything there. So I can just switch between those. It may prompt you after you run your first cell, so we'll see if that happens here. But basically, you can see here, yes, running with the cells of the VNVEV requires the IPy kernel package to be installed. So this is IPy notebooks is basically the underlying package in Jupyter. So we'll go ahead and install that and say, yep, go ahead and install that for me. And like I said, it isn't getting you massive amounts of errors here. It's just allowing you to run that. And you can see here is that I did install Geopandas again. You'll see these commands, these pip commands through the notebook occasionally to install different libraries throughout the series of the tutorials here. So that will prompt you to install the different libraries that you need. So first things first, let's just see what we have here. We can import the pandas library. And in most libraries, you have this underscore version underscore, which will tell you the version number that you're running off of. So for pandas, we're running off of 2.2.3. And for Geopandas, you can see here that we'll be running off of 1.0.1. Now, those are the two libraries because Geopandas is already bundled with pandas and uses those core things. We have, access to pandas and all the good functionality that comes with that. So it's already there as a result of installing GeoPandas. So the first thing we want to look at is actually importing these libraries in. So if you haven't worked with Python in this capacity before, this is a simple import statement. All I would have to do to actually import it would be to import pandas, and that would import the whole entirety of the pandas library, allowing me to do, like I said, these sort of functions here. But generally, most people, and you'll see this, they'll actually give it an alias. So it's import pandas as PD is, I think, the most common one. And GeoPandas is GPD because as you're typing your commands in notebooks, you don't want to write GeoPandas every time or pandas. You can just write PD or GPD, and that will help it, speed up and save you a few keystrokes here and there. So let's just go ahead and once we run these cells, we'll actually override the imports we ran up here. So let's import that and import that here, and then we'll be ready to go. So the first thing we'll do is we'll create a simple data structure here. And what we're doing is we're creating what's known as a dictionary type data type in Python. And this is if you're building a data frame from scratch, which you may occasionally do, but usually you'll be importing files, which we'll get to later in the tutorial by actually importing these different file types. But for now, we can actually show you what's under the hood here. So we'll just create a simple data set of different cities in different areas around the globe: New York City, Sao Paulo, Tokyo, Lagos, and Sydney, as well as their approximate populations, as well as the latitude and longitude approximate for those different cities. Now you can see here for the structure has this structure of a name, population, latitude, longitude, and then these square brackets that are passing in the different values. So if we want to think of this as a table, these are your column names, and then these are your individual rows. So it kind of looks vertically down here. And then we have the squiggly brackets that encompass the entire thing, which make it a dictionary. So let's go ahead and run that, and we can validate that. And you can see that the type function here, which just tells us what data type we're working with. Yes, this is in fact a dictionary. Now, if you haven't worked with dictionaries before, and this does become important because GeoDataFrames or data frames are effectively dictionaries with extra functionality around them. So they're not much different when you think about them from a Python dictionary. It just gives you a lot easier ways to work with and access and manipulate that data. So when we look at that, if we just wanted to get the name column, as it were, we can actually do that here by saying within these square brackets, access name. So just to validate that, we can actually just print out what data looks like here, and you can see it's the same as up here. And we just want to get access to that name column, which is here. You'll see it returns these values here. So we have New York City, Sao Paulo, Tokyo, Lagos, and it's within those square brackets. So what does that mean? What do those square brackets mean? That means that it is a list. So a list is just a set of different values. I believe they can be ordered or unordered, but there's, you can actually look at and access them based on the order, which we'll do in a minute. And it has different values in there. I believe you can mix the values, but generally, in pandas, you're going to have one data type per list or per column. So we'll get into that and understand also going forward what a list is and how it relates to a series or a geoseries in GeoPandas. So let's say I wanted to access this value for New York City, right? What I have to do is go once again to that name column, and then I want to get access to the first one so I can pass within square brackets again, this number is 0. So a list works off of a 0 base index, which means that the first value, which should normally be your number 1 value, is actually 0. So to get that, you actually get to the first value is 0, second value is 1, third value is 2, so on and so forth. So if I want to get access to that, now I have New York City, and you can see I've actually passed that into New York City. If I wanted to get Lagos, I would actually have to type in, I believe, 3 here, and then I can get access to that. So that's just another method of slicing your data and getting access to the data that you want. So now we want to actually turn this into a real data frame. So we're going to do that first in Pandas, show you what we have here, and then next in GeoPandas and actually create a geometric object from that. So to do that, you just use PD, which is that library. We're going to retrieve the data frame function. It's a sort of a class, actually, because there's lots of other things nested within that. So there's the data frame, and there's more functions there. But it allows us to just create a data frame using our dictionary. So since a dictionary is the base data type that we work with, all we have to pass in is the dictionary. And we can create that. I'm going to give it the name here and set it equal to cities.df. So now this object or this word or this text stores that cities data frame. So if I hit enter here, you'll see this looks like a lot cleaner of a table that we would expect from our data. So we have our name, population, latitude, longitude, and across here you can see our first row is New York City. So that's that 0 index I mentioned, population, latitude, longitude, which is great. Now, if I wanted to get access to just that name column, I can do effectively the same thing like I did up there. I pass the name, type in the name of the data object, in this case, our pandas data frame, pass in square brackets the word name, and that will give me access to just that column. So now I have access to that. If I want access to 2 columns, I can do what's like a double nested kind of filter here. So I pass in the first set of brackets and then a second set of brackets, the columns I want to retrieve separated by a comma. So if I wanted to retrieve multiple columns, I can actually do that here, and I can pull this in and actually say, okay, I want the name and the population here. So I first pass one set of square brackets, then a second, then all of the column names that I want separated by a comma. And that gives me a new filtered data frame for just those 2 columns that I care about. So let's move forward and actually now create a geodata frame. So we're actually going to build a real geospatial data frame from this. And just so we can kind of show you here is, once again, I'll use that type function. Now, data types matter for a lot of different reasons that I won't get into in too much detail here, but I will be using this type function, and just you can pass anything in Python into that and it will tell you what it is. So if I passed in the number 1, it will tell me here that it's integer. If I pass in 1.0, it'll tell me that it's a float. If I pass in the word hello, it'll tell me it's a string. But in this case, our object is you'll see here we have the pandas from the core section. It's a frame and a data frame. So that's what we have here. Now, to create a geodata frame, that's what I'll be doing here. So what I want to do is I want to create a new object. I'll just use GDF as my GeoData frame, which is my placeholder here. And I want to do very similar to what we did with pandas. I want to get access to that PD, or in this case, GPD dot. And instead of just data frame, we're going to pass in the GeoData frame. Now, there's a few different arguments you have here, and we'll review what this looks like. But in most cases, you'll probably be creating this from a file. So you'll be reading a file, and that will just return a geodata frame. So that's probably the most common thing you'll be doing. Sometimes you may have to create these on the fly, which you can see here. So I pass in my first argument, which is the original data frame we have. And then to create the geometry, I have this argument for the geometry here. I have GPD, and I have a function within this called points from XY. So once again, just to get access to those 2 columns that I want, which is latitude and longitude, or longitude and latitude in that order, I simply just retrieve that using those square bracket notation to say I just want the longitude column and the latitude column. One other thing I want to point out is that you can actually read some of the documentation in the notebook itself. So if you see here, I'm simply just hovering over this geodata frame. You can see here it has your arguments, which is the data, the geometry, and the CRS, should you need to pass the coordinate reference system as well. I'll show you what that looks like in a second. And it explains all of the different, the actual arguments you can put into that, the parameters, and then some different examples here. So it's really nice that you can actually have access to this right from the package itself. What's great is that it will actually reference the geodata frame here, and this will look basically identical to what you just looked at. So you can actually just see that right from here. Similar to this one, if I wanted to learn what the points from XY was, I can kind of hover over that and see what I can get from the documentation here. And you can see here that there's a function that tells me points from XY, and it has different pieces I have. I have an X value, my Y value, my Z value, and my CRS. So you can pass those in. So in that order, I have XY. If I had an elevation value, I could add that in here too, but in this case, I don't. So let's go ahead and just create our data frame by running this function. And you'll see now that we have a geodata frame. And what's different is these 4 columns here, these 4 first things look the same. But now we have this new geometry column, which has a point. This is a well-known texture geometry that's readable by you and I. So you can see here's point, and here's the longitude and latitude. Now, just to validate what we got there, is now we have turned this from a pandas data frame into a Geopandas data frame. So now it has that geometric object tied to it. So what can we do with this data? This function .info, you can pass this to any pandas data frame or Geopandas data frame. I like it quite a bit because it tells you all of the columns that are there, if they're non-null or null, the different data types that exist for each of them. So it's nice that you can see here's the data type for each of these. You can see here that number 4 is a geometry. Now, if I wanted to just get that geometry here, I can use that same square notation as well. You can also use this dot notation if the column name is a single word or there's no spaces or anything like that. You can do that here. It's going to get the same result. It just depends on how you want to write your code in this case. So there's no right or wrong answer to that. But I just wanted to point that out as well, as you can use that as well if you do see that. So let's just see what we get here. And you can see here that this is now this type of the geometry column is a geoseries. Now, I mentioned earlier that a data frame, both in pandas and geopandas, are basically dictionaries in Python. Now, a single column is not any different from a list. It's just called a series, right? So a data frame is made up of multiple series, as well as a geodata frame is made up of multiple series, as well as here a geoseries. So now we have a geoseries, which we've also added on. So if you go back to that picture from the beginning of the tutorial, you can see how all these pieces start to fit together, and you've built this out here. So let's say, once again, if I wanted to just get that first value here, you can see something funny kind of happened here. So instead of returning that well-known text, it actually printed out a picture. This is an image of this dot. So what does that mean? Well, there's a few different things. So let's take a look at what this type is. And you can see here that it's telling me it's from this library called Shapely. It's a Shapely, it's a geometry, it's a point, and the actual object is a point within the library of Shapely. It's in the geometry section in point, and the object is actually a point. Now, what does all of this mean? Now, Shapely is a library that allows you to work with geometric objects, right? So it uses under the hood this library Geos, which is in many other libraries, but allows you to work with geometric objects. So what you can do is you can create a point from these different values. Now you have this point value, and this is actually embedded inside of Geopandas, so you can actually use that there. So if I wanted to, you can probably just do this here. I can import Shapely. It's already there, and I now have access to that. So I have access to that entire library because it was installed with Geopandas. It's a dependency. Geopandas depends on Shapely. Now, Shapely is like a lower level library, and it's not to say that's not a useful library. It's just more under the hood, if you want to think of it that way. So if you're working in analytics or things like that, Geopandas should be good enough for you to work with. You may at sometimes need to touch the Shapely library. May or may not. It's hard to tell. If you're working with more of the data engineering side, you need to process the actual data types individually or do some things like that, then you may need to work with Shapely at a little bit lower of a level. So why did I take this pause? Because I do get this question a lot, is like, do I need to learn Shapely first before I learn Geopandas? If it's not obvious with the tutorial and the way we're going through this, Geopandas is generally very nearly good enough for you to work with what you need. You don't need to get too deep into the Shapely world of this. So I would work through Geopandas first and then determine that do I need to work with Shapely or not. And the good news is that if you do need to work with Shapely, you can use some of the AI tools like ChatGPT, Gemini, Claude, or any of the other ones you want to use to actually work with and get, programming tips or actually code snippets to work with Shapely, because it is such a widely distributed library. So with that said, I would work on Geopandas, but I just want to point out that, hey, we do have this now, this whole thing, this Shapely geometry, which is how Geopandas stores its geometries. So let's take a look at some other data types. I'm just going to create a string, which is going to store well-known text, which is the boundary of the state of Wisconsin. So it's just a very long string that contains all of the points that make that up. And I'll pull that in. I'm going to create kind of my very quick data frame here. So I have my data, which is the name of Wisconsin. I have my population, approximate population. I'm passing this geometric object into geometry field here. So go ahead and do that. Create a data frame from GeoData frame from that. We'll see here that this is the actual data frame itself. You see I passed in this function head off of the GeoData frame. Now that function will return the first 5 rows. This data frame only has 1 row. You can also do that in reverse with .tail if you wanted to pull the last 5 rows. But if you pass in a numeric value here to this, you'll actually be able to get more rows. You can see here from the arguments, it says the integer, the number is the 5, and then we'll return the first 5 rows by default. If you want more, 3, 10, 100, you can just pass that value in. But it doesn't matter because our GeoData frame is only 1 row anyways. So let's just see what this geometry looks like. Once again, we'll just pass and get to the geometry value and then find the first value within that as well. And you can see here that we actually have, this is still just a string. right? We didn't actually turn this into a geometry yet. So what do we need to do? Well, we need to create a GeoData frame again. We'll pass that data in and we'll tell it for our geometry column, we want to create the geoseries from WKT or well-known text. You can see here that will accept well-known text values and you can pass those in. So we'll do that here, recreate our GeoData frame. And now you can see here yes, we have this value for the state of Wisconsin here. You can see here it's plotted out, and this is going to be, if we do this here, type, it's going to be a shapely polygon instead of a point. Now this works for lines, multi-line strings, multi-polygons, the list goes on and on and on and on. So you can do all of those. But this is the fundamental underlying pieces of GeoPandas. So what are the takeaways here? First of all is that anything that works in pandas will work in GeoPandas. GeoPandas is based on pandas, so it gets all of that functionality from the core pandas library. 2 is that a GeoData frame is the core data structure of GeoPandas. That allows you to have your tabular data, everything else that's associated with your geometry, your names, your numeric values, your string values, whatever that is, an index, which tells you which row it is effectively. And then finally, you have your geometry. Now, a data frame as well as GeoDataFrames are made up of series. There's a Pandas series and then a GeoPandas Geo series, which is the geometry object. And a GeoData frame or a data frame is effectively a dictionary, and a series is effectively a list. And you access those different values using those bracket notations or the numerical, kind of equivalent for a list. So that's how you can access individual rows or values of data within GeoPandas or pandas. The last one, of course, is that Shapely is the library that stores the geometric objects in GeoPandas. It's not required to know Shapely to use GeoPandas. It's good to know that it's there and what's happening there, but is not required to know that, at least for a very early phase. You may want to learn it depending on your job role or job function and how much you need to actually manipulate those individual geometries. But we will show you more about that using GeoPandas and the extent of what they can do through the rest of the tutorial here. Okay, so go ahead and open the second notebook that's included in the downloads. So we'll go ahead and start that. We're going to take a deeper dive into some of the ways to work with geospatial data, including visualization to actually see your data, and then actually some other pieces for working with files. So once again, we're going to want to import our 2 libraries here, GeoPandas and Pandas here. And we'll just create that, or recreate, I should say, that data frame that we had before and the GeoData frame. So now we have our data frame here. Let's actually see what this looks like on a map. Actually, try to visualize it. So the first thing you want to do is, as I said, at different occasions, you'll need to install some extra libraries. This one is matplotlib. Now, matplotlib is a very visualization toolkit in Python that allows you to create image-based visualizations. So you can see all of the different plot types you can have here. You can do these and create many different types here, but this one will be a map data. I would also today call this a lower level library because of the work you have to do to kind of create these visualizations. Some libraries will build them for you, but these might require lots of different steps. So for this one, you can see here all the things I have to do to actually create this visualization. So it's not like a little bit of code. It's not a lot of code, but it's more than a simple command to do that. So I do call it kind of a lower level library for that reason alone. So we'll go ahead and install that. If you notice, I have this -q here, -q, whatever you want to call it. That will just create and install it quietly, so you don't have all the extra bits of, command output that we don't need, just to reduce the visual clutter a little bit. So what I'm going to do now is actually run this, and you can see here I'm going to create this, use this function .plot. So what this does is, off of the GeoData frame, what I can do here is create a visualization. So you can see here that's what it's going to do. Just have to access that off the GeoData frame. And now I have this very rudimentary visualization of my data. So you can see here that these are the different points on the map. We have our different cities here. There's no base map or anything. I have no context as to where this is in the world. There are some functions within GeoPandas to add base maps. So you can actually do that here. If you want to actually do some of the visualizations here. I can make maps and plots. So there's lots of things you can actually do with GeoPandas to make some pretty comprehensive maps. I think there's, if you scroll on here, there may be even like world maps and things like that. But I actually prefer different tools to do that. And I'll show you why in a second to actually see what that looks like. So what I'm going to pull in is I'm going to create a more comprehensive plot here. So you can see here is now I have some labels. I can actually label this and add some different things here. So these are the populations of these cities here on the map that we have actually created. But that doesn't do a lot for me. So what GeoPandas has implemented is this very simple function. If you just want to quickly see your data, you can do that with .explore. So gdf.explore actually loads that on an interactive map. So I need, as you can see here, I don't have a base map, and this error was here intentionally. The reason for this is we need to set the projection. Now we'll explore projections in a little bit more detail later. So this is just kind of a quick aside to see what that is. So if I go to GDF and I want to see what the CRS is, I can go to CRS here. And you can see here that nothing got returned from that. That's because I haven't set the coordinate reference system. So I need to do that. I have a function here called setCRS. And I can see the notes here is that I can set that to a few different ways. I can basically pass in the EPSG code with an integer. I can set it with the string. There's a few different ones that I can set in here, but we'll just do it this way. I usually go like this, using string EPSG and then 4326. So that will actually set the projection here. And just to validate that that did work, we'll try this now. We'll see if that has a CRS. You can see, let's try this. I actually have to reset the object here, GDF. And I should have now a 4326 EPSG. So the problem which I didn't, I just ran the operation. I didn't set it to reset the object. So I need to reset it. It now has that new projection system. I can also go like this and just use the integer as well. That works just the same way. There's no right or wrong way to do that. Just depends on how you want to do it. And now, since it actually knows where to put our data, we can see it on a nice map here. And this is just an interactive OpenStreetMap map. And yeah, you can see here, here's our points that we placed in, and you can actually hover that over that to see the population and things like that. So this is great for very quick and dirty, exploration of your data, just to see it on a map, make sure, okay, everything checks out. That's why I like this explore function. It's pretty simple, straightforward, just for exploration. Now we can do a little bit more here as well. So I'm going to import a few other libraries. One is Folium and one is Map Classify. So go ahead and install those here. And you may need to install those to get the explore function to work. I did have to do that the first time around. So if you do need to do that, you may need to update that, and that will get you all set up there. You may also need to install this library IPyWidgets. And I just have the U function to install that as the user across the core user group. So you may need to install that as well. But the next library we're going to actually use is LeafMap. So just run these installs, make sure everything will work fine and comparably to what I'm doing. The nice thing about these virtual environments is that they're kind of blank slates. So they just, will run just fine with what you need. So you should be able to work with the same things as I am. So let's take a look at LeafMap very quickly. So LeafMap is a fantastic library that adds in lots of different features, but integrates many different visualization platforms and analytics platforms into one single library. So as you can see here, it's for geospatial analysis and interactive mapping in Jupyter. It's maintained by Qisheng Wu from the University of Tennessee. He's also another YouTuber here if you want to check out. He has a million tutorials on LeafMap, and you can check out a lot of different things. Like I said, here's the YouTube channel. So you can actually go through and there's lots of different things here for LeafMap, as well as this other library, GMAP, GEE for Google Earth Engine. But this will actually walk you through tons of different notebooks to use all these different pieces. There's a lot of functionality packed in here. And when I say a lot, I don't mean that, I really do mean that. There's a lot of things you can do here. So you can see all the different pieces, but it allows you to create, one simple thing it does is allow you to create interactive maps with a lot more functionality within them, which is what I like. So to do that, what we'll set up is we'll pass in a new map with the center at 2. Oh, sorry, I need to actually import the library to make that work. And then to return that, if I just return that object C, now I have a map here, which is similar to our map up above, but we have more things here. I can actually, it's more of like a comprehensive mini GIS inside your Jupyter notebook, right? So I can do drawing, I can, integrate with raster data here. I can actually open local files without importing them into Geopandas. I can change my base map to many different types. So if I wanted to pull in, you know, any of these different maps, I don't even know what all these are, I can pull that in here, and you can see here that I have now my new base map type here that I can pull in. And so you can pull in any of these different types. Oh, it looks like I need that authenticated. Some of these do, but let's see, there's a USGS topographic map here, which we can pull in as well. So there's lots of different options for you here. So that's really nice. Usually it just comes with the base OpenStreetMap one here. And that's usually what I think most of them use, is that OpenStreetMap. You can also add in Google Maps and things like that. So it really depends what you want. But yeah, that's just the simple map object. To add data, we're going to basically add a GeoDataFrame and pass in our layer name as points. So I'll run that here, and you'll actually see that if I zoom out, it's actually added that back up to the map here. So you can see here that here is our data, like just kind of what we had before, but as points on the map. So it's actually updating the original map. So I can also, change and add the base map here. So I can modify that if I wanted to, avoid using it with this. I can just kind of do that with the code as well. So it's all going to keep updating that same thing. And then what we can do here is, if we just wanted to look at our map here as well, and if I want to add a pop-up, I can do that here too. So that will now add a brand new pop-up in. I can actually click on these. Now, for some reason in my notebook here within VS Code, it doesn't like the pop-ups. I didn't actually figure out a way to work around that yet. But if you load this into a different notebook service, it should work just fine for you. Okay, and there's one more visualization library I wanted to point out, which is Lawnboard. Now, Lawnboard can be accessed, I believe it's in LeafMap as well. So there's, LeafMap kind of has everything. But Lawnboard is a library for integrating. So Lawnboard allows you to visualize sort of larger scale geospatial data sets in Jupyter. And it uses some unique technologies under the hood, like GeoArrow and GeoParquet, as well as some of the GPU-based map rendering libraries. So it allows you to do that very efficiently for much larger data sets. And we're just going to actually use one of their examples. So I actually just replicated the speed test data example here. So if you want to do this one on your own, you can do that. But I just wanted to show you that because the data we've been working with is so far 5 rows, which definitely doesn't fall on the large scale side of data. So what I'll do here is I'll actually import all these different libraries here, and then I'll collect this data, which is this is the cell service, or sorry, speed test, internet speed test data from Ookla, which is made available via AWS. So this is just a data file that's hosted on AWS. So that's the file here. And then what I can do is basically create a GeoDataFrame from that. So we'll cover a little bit more about this code later, about how to actually do this. You can see I'm creating first my, to break it down, I have my first column here first row to create the GeoDataFrame. Then I, basically create some of the different tiles and centroids and things like that. So I set up my GeoDataFrame, and then I can actually pass that to a Parquet file. Some different steps here that are happening in between, but for the purposes of this, sort of tutorial, or this section of the tutorial, I just want to give you a quick overview of what you can do. Which the key here is that you can actually add in and create a layer from Geopandas. So if I jump down here, you can see you can create this scatter plot layer, which is one of the layer types from Geopandas, and then pass in my data frame, and then simply return the map here. So let's just take a look at our data. You can see here is that I have the point, the latitude, longitude, and the average download speed here. So that's what I'll get. To actually create that, I'm going to go ahead and just run this command to create the layer, first of all, and then add that layer to the map. And I'll be able to visualize my data. And that should, if I did everything right, give me my map here, which is great. And I can see here, this is an interactive map. And I can get all that speed test data that I want to take a look at. And you can zoom in and out and see what's actually happening in these different areas. So these are our different observations that you should be able to see here. And if I zoom in, you should have all the different points here as well. So that's just giving you a very quick view, just because it's just trying to show like a scatter plot at a very high level. We didn't add much to that. But let's actually run the rest of these commands. We'll get the average speed compared to the area around it, and we'll normalize that, give it a color ramp, add that color ramp to the new column in the field, which is what we're doing here, layer.getFillCover, and apply that. And then run the layer.getRadius. And then I believe if we return the map again, we should have that here. And then this will show it with those new values in there. So There are a few other steps we perform to basically transform the data, change it to the normalized download speed, and then apply a color ramp to it, which you can see here. So as I zoom in, I'll actually get a much better view of like the outliers and the download speeds compared to other things. Now with Longboard, you can add some other functionality like pop-ups as well. But I just want to give you a view of like how big you can go with your geospatial data visualization and different pieces, which is quite comprehensive within a notebook service here. And it's all under the hood using a GeoDataFrame, which is the same technology. So you can see how extensible Geopandas is to go from small data up to very, very large data sets. So this is probably a more advanced section here if you wanted to get into that, but it's code so you can actually showcase it and run it and see what that looks like on your machine. So I wanted to give you just a view in terms of that as well. But that covers this section, which is the visualization components of Geopandas and the extended libraries that work with it well. We'll go ahead and jump into the next section. So crack open that third notebook and we'll get into that as well. Okay, so moving on to this next section, we are going to take a look at how to load data from common geospatial file formats into a GeoPandas data frame. So effectively reading files as well as exporting some files as well. All of the data we'll be looking at comes from the New York City Open Data Portal. So we'll be pulling several different data sets from there to take a look at. And ultimately, we'll be using these data sets in our final projects as well. So you can kind of get familiar with these data sets as we use them. So when we actually come to the project, it'll be pretty familiar with what the data is. Okay, so as always, we want to make sure to load our necessary libraries here. So we load in GeoPandas and Pandas. And what we're going to do is read in a shapefile. So all the data is in this data folder. It's the zip file that you downloaded from the course website at moderngis.xyz. So if you have that, you just want to make sure it's in the same location, the folder itself, the data folder is in the same location as your notebooks. So that's because it will run and reference these names. If not, the data may not load correctly. So you'll just want to make sure it's in the right location. So first things first, what we'll be doing is we'll reading a shapefile. So I'm going to give it the location of that file on my computer, which should mirror what you're doing on your computer as well. And you can see here that's in this data folder. And I have within that the shapefile for the pedestrian zones. These are designated walking areas within New York City. And then in there are all the necessary files for our shapefile. So if you look at, we have our different files that are tied up in that shapefile folder. So I'll just move that for now. And what I'm going to do is I'm going to use this function read file. This is a pretty extensible function because it can read so many different file types. So as you can see here, the function allows us to read the file name, which is the folder location where it lives. You can limit it to a bounding box or sort of mask it. You can pick the columns, rows, things like that. You can also pass in an ability to use an engine, right? So currently Fiona, which is another lower level Python library to work with vector data, to work with that. So that's the one by default. I haven't encountered too many times where you need to actually change this, but in case you do, it is in fact there. So you can see it's a really simple function. If you don't have, much data or things that you want to kind of filter or adding some of these different arguments like a mask or things like that, it's basically just the folder location, which is what we have here. So I'm going to do is then hit that here, and as you can see, I ran 3 commands in one cell. Basically set a object as shapefile for the location of the folder just to keep it neat. I pass that in to the GeoData frame, and then I return the head of that data frame, which would be the first 5 rows. So you can see here, we have, the borough name, where that's located, neighborhood name, the zone name and geometry. And then we can actually, once again, just explore, take a look at where that data is. We'll create that on the map here. Oops, I went too far down. And you can see here that this is actually the different pedestrian zones. So you can see where these are designated here within the city. So that's the first bit. It's quite easy to load shapefiles. You just need to expand the zip file where the shapefile comes, open it up, and then you're ready to go. GeoJSONs are also fairly easy to use as well. So, I mean, the basically, as we go through these, you'll see all of them use this read file function. There's not much different there. What is different is that this is actually from a URL. So this is a set of New York neighborhoods. The data is actually, I think, it's not the official designated neighborhood tabulation area as defined by the city. But as I'm sure you know most cities define their neighborhoods themselves, and I think this actually does a much better job of showing what anyone might call these particular neighborhoods. But what's great is this is just at a URL. This is actually a file that's hosted on GitHub, and I can just reference to that directly, that GeoJSON file, and it'll work just the same as if I'm pulling in something locally. So I pull that in here, and then we can actually load that in to the map. And you can see here that here now we have our neighborhood areas, and these are kind of referenced as we have them. So we have the different neighborhoods here that we can click on, which is great. Okay, so same thing. You can also read in geo packages. I just want to give an example of this is different rivers globally. So same thing here. I'm just going to read everything in and then just hit explore. And as you can see here, here are all my rivers. So this is once again a remote file, a remote geo package that I'm reading in, and I'm picking that specific, folder layer there as well. Same thing with so we can do the same thing with a flat GeoBuff file as well. Once again, this is a hosted, meaning that it's on a URL. So I can actually pull that in. And here I can actually see the US counties data set, and that will load in. And like I said, it's nice because it's just pulling directly from, a remote URL where I can read that in from. So you can see all the different US counties here as they designated within the United States, which has been really nice. So that's kind of the first pieces that make it easy to load files in is that read file function. Notably, you'll see that Parquet is not listed there, and we'll talk a little bit about why that is in a second. But I also want to cover in some other ways to connect data, which is in the databases sort of functionality. So we'll take a look at two ways to do that. One is with PostGIS, and then the other is with DuckDB and how they kind of work together. So here's just a quick example of what a PostGIS connection would look like. And you just have to basically set this up, and then you can read that file, or sorry, that query in as a GeoDataFrame, which is quite nice. So what you need to have installed is basically this library called SQL Alchemy, which allows you to create a connection string to your Postgres database. So if you see here, I have, these are just example parameters. If you have a Postgres database, you can set that up. I can't build one for you, unfortunately, but I do have a video here. If you want to build one, you can take a look at that and then pass these parameters in. So you have to set up your host, your database, your user, and your password, and then pass them into a connection string that looks like this. SQL Alchemy will then use this create engine function to create that connection to, or open up that connection to the database. And then you can pass in your query here. And you'll see what you notice here is that this uses a different function called read PostGIS, where you have a SQL or query that you're passing in, the connection, which is the connection to the specific engine, which you established up here. So it's going to connect you to the database, the column name, the name of the geometry column, which could be anything, depending on what you want it to be, and of course the projection. So this is basically what this will look like if you were to do this yourself. So if you want to try setting up a Postgres database and load some data in, check out that video I linked earlier. You can give that a shot, and then you can go from. Now, on the other hand, we also can work with DuckDB to read and work with geospatial data and bring it into a data frame in Geopandas. It requires some like one extra step, but it's not that complicated. But the advantage is that you can simply install DuckDB as a Python library. So what I can do here is I'm just going to install this using pip install DuckDB, like you see here, and I can actually directly initialize a connection. So DuckDB has a few advantages. It's an analytical database, meaning it works with larger volumes of data for analytical questions, like for in the spatial world, maybe like a spatial intersection or an aggregation or something like that. It works very well with those types of queries. It can read files directly, so you can actually read it from files, and it's an in-memory database, which means it works on the memory of your computer, and you don't need a different infrastructure or container or virtual machine to set this up. You can kind of just do it in the context of your computer or your notebook, which is really advantageous. Now, you can do this a few different ways. I like establishing this connection. You don't have to do that. You can just write a query against DuckDB in memory, but this allows you to just create that connection, and that allows you to store a few things as well. So I think it kind of ensures that you get all those different pieces right. Now, what we need to do is load in the spatial library, which is a open library that extends DuckDB. So you just run these two things. You're writing a query against the connection to install spatial and load spatial. So that should run relatively quickly. And then what I have here is a query that I'm going to be creating. So what I want to do is actually read some data that's remote. This data is actually bike trip data. So that's data from New York City Bikes, which is the bike share program there. And it has the lat long of the starting position and the end position of every trip that's been taken. This specific subset is from 2024 in June, which is what '06 means. And this is open data again that I can access, and DuckDB can read this as a remote file. What you'll notice here is that it is a zip file. So it's a zipped up CSV file, which is kind of the strange part, and Geopandas might have some trouble with that. So we're going to handle some of the processing bits in DuckDB and then read that over into Geopandas to take that further. So what I'm doing here is I'm basically selecting the column, or sorry, the column 9 and 8, which contain the latitude and longitude. They're not labeled correctly in the CSV, unfortunately. And I'm creating a point from that. And then I'm just going to return that as text, as well-known text, to pass that in. So you can see reading that using these two SQL function, st as text and st point, to create the point and then turn it into text. So that's our query there. And we can actually go ahead and execute that query here. So it's going to query that and effectively store that in this DuckDB df here. So it's running the query from that I passed up here, and I'm turning it into a data frame, as you see here, using this .2df function. So that allows me to create it as a data frame and hold that in. So it's just turning it into a data frame, and that's where that data will be stored. So once I have that, the data should look like this here. So I have different unnamed columns, which is unfortunate, but that's just the messy nature of some data. It looks like that. So it's actually good to get your hands dirty and work with data like this. So we have, your different columns here. This is the identification number of the trip, unique identifier, the bike type, dates, should be start time and end time, the station where it was taken from and to, and then of course your latitude and longitude, which is kind of what we care about and use here. And then you can see here we have the geometry column, which is the point location of that, but in well-known text format. So we'll see why we use that in a minute. But if you remember, we can always use the well-known text transformer in Geopandas to turn that into a geometry. So what I can do here is I can create a new data frame, or DuckDB GeoDataFrame, and then use the geo series from WKT, using that bracket notation to retrieve just that geometry column from what I returned before. So once I run that, I'll be able to see the data here that I have. So that whole transformation step took 3 seconds, which is pretty quick. When I take a look at the info of what I have here, you'll see that I have about 4.7 entries in the data set. You could see the different data types, and then in fact we have our geometry here. Now what I'm going to do is show 100 of these records here. It's pretty simple, because what I'm doing here, and I'll just sort of illustrate this, is instead of taking the whole data set, what I'm doing is just taking the first 100 rows using that head function, the header function, to get 100 rows. And what's important to know is that this is just returning a data frame, or GeoData frame in our case, right? So it has all the different pieces you can access from that, including this explore function. So instead of writing multiple steps, I'm just going to wrap this all into one function and run it just like this. And then from here, I'll be able to see those first 100 rows and the different trip identifications about that data. So the same thing, we can actually use that with geospatial file types as well. That was just a plain CSV file. But here I have that same neighborhoods file here, and I'm using this function within DuckDB called stread. So it allows me to read a file type. So I will read that in. I'll get the first 10 rows or the first 10 neighborhoods, and I'll do the same process here. I'll pull those all in here, and I can actually, what's nice about this is I can see here what I get back from that. So let's go ahead and run that with the connection. We'll run the query and turn it into a data frame, and then see the first 5 rows that we get back. And you'll see here I have this kind of strange data representation when it comes in from a data frame with the geometry data type from DuckDB. So it's a little bit strange, but that's okay, because we can just transform it using STS text. So all of this bears the question, I think this is probably what you might be thinking, why would I be using a database tool or SQL in Python when I can do all the same things in Python? There's a few different reasons why you may want to do that. You may want to commingle different file types there. You might want to, kind of shrink the data prep process down into SQL, which can be more efficient. Sometimes doing analytical queries like the one I'm going to show you can be a little bit more efficient in DuckDB compared to something like, so that's what we're going to take a look at. What I'm doing here is basically creating a more complex query. So I'm going to do a spatial intersection and aggregate. So I'm going to count the number of trips that come in. I'm going to return the neighborhood name and the geometry of the neighborhood name. So the first thing is I read in my neighborhood files here, or sorry, my neighborhood file, which I'm using an alias of n for that table. So n represents the neighborhood tables. In this case, I'm using read CSV, which is going to B for bikes, and that every time you see table B, that's the bike data. So here you see I have the count of the bikes, the neighborhood name, and the geometry of the neighborhood from the neighborhoods file. Then what I'm going to do is run this st intersects. I'm going to join those two on the intersection of, or anytime those two intersect, the geometry of the neighborhood and the starting geometry of the bike trip. And then I'm just going to select them from a specific date. So I'm just going to do some casting and translations of the dates here. Like the data type stores as a string. I just need to translate it to a date. And I'm going to pick 15th, 2024 to be our date. And then I'm just going to group all the data here. So that's what we're going to do. I'm going to go ahead and run that query to do that spatial join. And this should be a little bit faster than doing that in just pure Geopandas. Geopandas join performance has gotten significantly better. So it's definitely doing a lot more from that perspective, but you would also have to do some date filtering and this and that. And I guess the biggest thing is you would have to have all of that data in a GeoDataFrame in memory to do it. You may or may not want to do that depending on what you're trying to do, because it can take more time to read that into memory. And that might actually make it take longer at the end of the day, which is maybe not just the join itself, but all of the other stuff of getting the data in and filtering and things like that might make it take longer. Now, of course, this depends on you knowing SQL, but like I said at the beginning of this tutorial, I want to give you this ecosystem of tools to work around with Geopandas so you can really start to extend and go forward from there. So it looks like our join completed here. And what we can do now is we have this neighborhood data frame. We're going to obviously use the geometry from that to turn that into the proper geometry. We can see our values here. So we can see all the different values in our actual geometry value, which is going to be the one that we need to use to map with. And then we can just explore that data here. So you can see here that we can get the different counts from these different neighborhoods, more in Midtown and different parts of Manhattan compared to some of these areas out in Queens, even in northern Manhattan and things like that. So that's the combination of using GeoPandas to go, or sorry, DuckDB to go a little bit further. You can take your data a little farther. Hello. Now, for our final one, you can actually see that we're using a GeoParquet file. This uses, once again, another separate function called readParquet. So to take a look at this, you can see that there's a bunch of things that we can do here, similar to what we've had before. We have our path, our columns, some of the storage options. It's a different one, so you can actually use that if it's data in a cloud storage bucket system like Amazon, AWS S3, Google Cloud Storage, or others. And then there's all of these other arguments in this PyArrow read table. And that's what's important to kind of call out here. And we'll just take a brief look at that to show you what that is doing specifically. So this gives you a lot of options to how to read your Parquet file. So there's different things like, is there a partitioning system? What type of filters do you want to use from that partitioning system and things like that? Without getting too much into the weeds here, and Parquet as a topic is something we could talk more about as a file system. But basically, there are some different ways that you might partition some data. So let's take a look at an example of that to make it a little bit clearer. So this is actually a data set. Calvin Liu put this together. It's a great data set that takes that city bike CSV data that we're working with and puts it in a Parquet format. Now, what you can see here is that it has a set of folders that break it apart by year, 2024, 3, 2, so on and so forth. This is known as a partition because it's partitioning by the date itself. So if I go into 2022, you can also see the month. So January, then 2, February, March, April, so on and so forth. It's breaking those apart. So what I could actually do in that filter piece, so if I go all the way down here to filters, is that I could actually create a filter based on those folder types. Now, what's nice about this is that it's going to ignore all the other data based on the filters I put in. So if you have to filter a large data set, this is a way you could do that very efficiently before even loading in the data. And that's one of the big advantages of GeoParquet. First of all, it's a smaller format, you can compress a lot of data into one place, but most importantly, it has these partitioning features that make it very efficient to read. So going back to the code here, I pulled in this data set, which is the of field boundaries in the Canary Islands. That's a part of Spain. And you can see here that I actually pulled all those in and pulled this in as a data set here. So briefly, if we just want to explore that, since it's a large data set, I'm just going to pull, once again, 100 rows. And you can see here we have our different various field boundaries on top of the map. So that's the way you can use read parquet. It's a different function, just like read PostGIS is in this case. So that kind of covers the section on reading files. We'll jump into the fourth notebook. All right, so in this section, we're going to look at functions you can use to operate on your geometry. These are some of the things like areas or intersections and stuff like that. So we're going to introduce a bunch of data sets now from that New York City Open Data Portal, some of which you've seen before and some of which are new, but that will actually help you understand and how to work with these different operations I'll be performing. And also these are some of the data sets we'll be using to go through our final project at the end to kind of do some different spatial analysis. So as always, I'm going to import my libraries and then we are going to read in 4 different files. So you can see here, I'm using the read file function on all of these. We're going to pull in New York City schools, the point lat long locations of those schools, subways or the subway entrances, because there's different multiple entrances to a station, bike paths in the city, which is you've seen that data set already, and then parks, these geometries of different parks. Once again, this is all from the New York City Open Data Portal. So we'll read all of these files in, and then what I can do is just quickly visualize them to explore this. So this is the school. Obviously, you can see all the different school locations here. If you hover over them, it'll give you the name of the school, which geographic region it's in. So these are the school districts, as it were. So that's the schools data set, the subway entrances. So you can see here, if you look at this is one station here, but there's multiple entrances. So you can see the name of it, the First Ave at 14th Street Northeast corner. And then this is the other one here. So there's different entrances all along this area to get into this one station. Here are our bike paths. So these are all the bike paths that go through the city that provide safe bike access. So you can see here where those are. Some of them are sort of more recreational. As you can see here, these paths in a park area, and some of them are for transportation to get around the city. Finally, we have all of our park locations, and these are all of the parks in the city, all of the small parks in the different neighborhoods, all the way up to Central Park, which is, I'm sure many of you know, or have at least heard of Central Park. So the first thing I want to do is I want to get this into a projection that I can use to get proper measurements in. So we're going to use 3857 to do that. That will give us the ability to work in meters and not degrees. So to do that, I just quickly reset the data frame using that toCRS function to change it for each of those, and then I should be good to go. I'm also just going to import pandas and use this display function. Now, sometimes with very large numbers or numbers that have a lot of decimal places after them, it defaults to scientific notation in pandas. So this is just to suppress that, returning 4 decimal places at max, so we can actually read the numbers we're looking at. Okay, so the first thing we want to do is review the area. Let's say we want to get the area of each of these neighborhood boundaries. Now, to do that, I'm going to do a few things in this command here. So let's break this apart because I'm going to be using this process each time. On the neighborhoods data frame, if we take a look at it now, I'll just go up here and we can just get the layout of that data using .info. And you can see here that there's 5 columns, but there is no area column. Now, by doing this, I'm actually going to create a new column called area. Now, if that column already existed, this operation would overwrite that data. So it's setting that column area using that bracket notation equal to the value I'm about to give it. Now, if we look at it here, neighborhoods.geometry, remember that if that dot notation is just, it's the same as using a bracket notation. There's nothing different. So just to prove that out, I'm going to go up here and I can show you neighborhoods and geometry. and that's going to return all the geometries there. And then I have a set of these that I can access different values off of this geo series here. In this case, I want to use area. And what that's going to do is it's going to go over each one and calculate the square meters of each of those neighborhoods. So that's all that's happening here. So in this command, I'm just basically creating or designating a new column called area, giving the neighborhoods.geometry.area and setting that area value equal to that here. So what we'll do here, as you can see here now, I have that value area, and that is actually permanently tied to the neighborhoods here. So now you can actually see it up here as yes, it did in fact add that column. So if you want to keep that column, you can get access to it that way. So for this one, we're going to get the boundary of the park, right? I basically want to get the boundary of that park, or basically the line string geometry that represents that park. So just take a look at, this is all the data we have here. There's a lot of data that comes with this data set. So there's a lot there. And I'm going to do the same thing. I'm going to get the boundary off of that, right? If we just run this command alone, we should be able to see that here. And it will say, yes, this is a multi-line string. Now to map this once again, remember we have to be in that 4326 projection to use our explore function. So I'm just quickly create a new data frame called parks mapped, set the CRS equal to 4326 to explore it. So you see me do this a few times. I'm just going to explain it now so we can keep going so I don't have to break that apart every time. But now you'll see that I just have a set of line strings, which are the boundaries of my park. So it's actually, you can see how quick and snappy this is. It's very easy just to say, I need the boundary, I need to grab this. You have all these accessors passed off of that. You can also get the total bounds. This is just another one of everything in that area, the bounding box of the entire data set. So this captures every geometry in that. There's just another accessor there called total bounds. Now I'm going to create another data frame here using the 2263 projection. This is that's specific to New York State, Long Island, and so it will return data in feet. So if we want to use the proper projection there, that's the one that usually comes with most New York City data, uses this Long Island projection for feet. So for the bike path, if I wanted to get the length of that path, I'm going to actually see which is the longest path. So I can see here that this segment is the longest, and it's about 2,000, almost 2,200 feet long. You can see there's also segments that are about half a foot long. So, there's actually very small pieces of these bike paths in there as well. I think that's more just how the geometries are divided. So that's what we're going to do here. So what first thing I'm going to do is I'm actually using my bike paths, my original data set. So this will return in meters, right? So this is the metric version of this. So I can see that this path is about 20 or almost 2,200 meters long. I can do the same thing with the feet here. So even though this is running the exact same operation, I'm just using the different data frame. This is now returning in feet. So it's 5,400 feet. And just by changing that projection, I can get a different calculation because that geoseries holds that geometry and the projection, CRS. So I can get different values based on what CRS I'm using. So what I'm doing here is I'm going to just filter to this piece that is the longest segment ID, or this long segment ID here, which is 33185. And there's some different kind of filtering that I'm doing here. So this may look a little bit complicated, but I'll just break it apart. So within this, what you can actually do is if you want to effectively filter a data frame, let's just say we want to do this here. Maybe we want to get a specific neighborhood. So let's start with that. Neighborhoods. And within that, I use the bracket notation. I call neighborhoods again, and I pick the name, which is going to be the neighborhood. So to write neighborhood 3 times. And then I want to get a specific value. Now in Python, you want to use double equals to represent equality. Single equals will reset a value or an object. So that's why you said double values to represent equality between 2 values. And let's just get Chelsea, the neighborhood of Chelsea. So that will filter that data frame down to Chelsea. So that's all that's happening in this first bit of the code. I just have to change it to pull, because in the segment ID, it doesn't store as a string for some reason. So this just had some weird data type issues. So I'm basically taking the segment ID, turning it into a string, and then evaluating it as a string here. Then I'm going to set the CRS here. I'm going to set that to 4326 to quickly map it. Allow the override so I can actually overwrite that geometry CRS, which is just another argument on this set CRS function. So if we hover over that, we can actually see what's going on here with that set CRS function. Oh, it doesn't give us the full documentation. Let's go back here. So you can see it will do this allow override here, which is just saying that it will, in fact, override that default projection that's already set to it. So this will then show us that longest bike path. So now that you can see that we have this ability to filter, this is all I'm doing here is this filtering, where I'm basically saying bike paths, then bike paths segment ID, and I just have to turn it into a string. So I'm using this the as type operator here to turn it to a string, and then evaluate it, which is this 299972 is the unique segment ID of the longest segment, the longest bike path segment. So I then change that CRS here. It's coordinate references into 4326 to map it. And you can see here, here's that longest section, which goes through Fresh Kills Park in Staten Island. That's the longest continuous bike segment, at least as it's mapped. There might be longer paths, but the segment as it stands here from location to location is there. And you can see here, it has different metrics here from the to street to the from street, and it tells you the different streets it runs to, and then the street it runs along. So you see from street is Richmond Hill Road, to street is Arthur Kill Road. So you can see here Richmond Hill all the way up there, and then at the bottom there you should see Arthur Kill Road down here somewhere. So that'll be the where it ends to, and then that's the complete segment of that data. Okay, so now we're going to get into a little bit of some more advanced spatial analytics using Python. And that's what we're going to do to find the shortest distance from a school to one of our subway entrances, right? So to break this apart, let's just go bit by bit. We can kind of review each line as we go along because this may add some complexity. So we have our schools here, which gives us the nearest subway distance, right? That's going to be the new column where we store that data. So pretty straightforward. Now we are actually using this .apply function. So on our schools.geometry, we're going to use this .apply function. What is the apply function? So if we look at the documentation, it basically, we can create a function that will perform some sort of process and apply it onto our data, right? So let's just come up with a simple example here. So we have schools. Let's just take a look at our data here. And you can see we have this geographic metric here. So that's the zone it's in. And you can see it's an integer 64. So if I wanted to, I could go schools.geographic.apply, and we could pass in any function into this apply that we want to. So let's create a function. So we want to create a function called def add one, and we're basically going to simply return the value that comes into it plus one. And that's all that it's going to do. Now, all I have to do is basically pass in that name of add one, and it should just apply that across that. So it's going to add that up. So that's all that it's doing, is taking a function that takes a single argument and passing that value in. So that's all we're doing there. What we're using is just a lambda function here, right? So this is a lambda function, which is basically a temporary function. And this is saying that it takes for each school, right, where each geometry here represented by the name school, could find the subway and the distance to the school, and then find the lowest possible value, right? So if I was to say subway distance to every school, it would basically do a cross join of all of them, right? The lambda, so we would basically say if we wanted to find one specific school, we could certainly do that. So let's just test that out, okay? So maybe we have a school, and we say schools dot head one, and that's our one school here. Now, if we want to find the distance to all the subways, we have subways, distances, and then we have our one school dot geometry, and we can get rid of them in here. And then that would calculate the distance to all of those different school locations, to all of those different places. So that's kind of what would happen there. And what we're trying to do is find the smallest possible value. So that's it may look a little bit more complex here, at least as it reads. And that lambda function can be a little bit tricky. Let's just break that one down as well. So if we have a lambda function, it's basically a temporary function where we take x, and then after the colon, we return x plus 1. Now, in our example from before, if we had, let's take our schools dot geographic dot apply, we could simply pass this lambda function in here, and we would get the exact same result. 2, 2, 2. This is obviously 1, 8, 12, 10, so on and so forth. So we could change that to 500, and we would get 501 and the different values there, so forth. So that's all the lambda function is. And it's just saying to take the school, find the distance to the nearest one. So we can run that, and that's actually quite quick to actually get that back. And we'll sort this by the subway, or sorry, the school that has the shortest path to a subway, which is PS 150 in this case. That's what we're looking at. So basically we can see PS 50 is the closest to a subway entrance, not a subway station, but a subway entrance. Let's actually see if we can take a look at that on a map. So there are actually several PS 150s. There's one in each borough apart from Staten Island. But the one we're interested in is actually down here in Lower Manhattan. And you can see here that this building is PS 150, and then we have a subway entrance right here. So very, very close to it. I don't know if it's measuring this building as well, but effectively that's what it's giving us. And we can measure probably from the corner of here all the way to here that it is about 23 feet. And I think it told us it's about 18-ish feet or meters. I can't remember what it is in, but not far by any stretch of the imagination. So it's pretty close. So another common use case is to create centroids from geometries. This case, we're just going to do a quick combined function here, take our neighborhoods, geometry, centroid, and then explore that value. You can see here now all my neighborhoods are turned into centroids. Pretty straightforward there, as you just turk that in there. Same thing with bike paths. You can apply buffer, and then buffer actually has an argument to apply the units beyond that. So in this case, what we'll be showing is the bike paths geometry with a 10-meter buffer around each bike path. So you see those all have turned into polygons there. And what we want to do is we want to basically showcase what that would look like on a map here. And then we just take a subsample of that. And you can see here that these are now not just paths, but fully buffered, geometries here. We could, just to see what that looks like, if we wanted to change the buffer to 100 meters, you should see a little bit wider of a buffer there, which is exactly what we would expect. So it's just taking, once again, all these are operations on the GeoSeries, which is that effectively list of data in Python. So let's keep going. Let's take a look, in this case, all the parks. So we're going to do an intersecting analysis here. So we'll take parks geometry.apply, which is that first part of the function that we're doing here. And then we're going to do our lambda function here, which takes any park, which is the geometry, the park geometry, and say the bike path.geometry intersects the park. And if any, the .any operator will allow us to see if any of those actually intersect. Now, this is just a built-in function, right? This is just any is a built-in function that is tied to lists. Once again, I want just keep reiterating that a series is basically a list, and then you can use pandas functions or Python functions on top of those lists. So let's just go ahead and run this, and we'll see here that they'll find any paths that intersect a bike path. So now we actually can see that. Let's get the parks value here, and all the way at the end, we should have our new column, which can tell us if it does intersect a bike path. True, false, false, true. And basically, it's that function returns a true or false if we do that. Let's find all of the paths that match true. So like I just said, to do that filtering within a data frame, but still return the whole data frame, we take parks. Inside of that, we pass the filter value, which is we want to filter this column, parks intersect bike path equals true. And then we'll just briefly explore that. And you can see these are all the parks that intersect a bike path that have them. Now, this is kind of an interesting one because this highline is a raised park, so the bike paths go underneath it, but in fact, from a geometric perspective, that does intersect, so that checks out. We also can do some cool things like a minimum bounding circle. So the minimum bounding circle containing each park is here, so you can see the circles, and you can kind of do that if you wanted to do that. You can also create convex hulls. So these are the convex hulls of all the neighborhoods. You can also simplify your data. So if we wanted to simplify our geometries for our neighborhoods, this is the result of that simplification. So it's a pretty slight, small simplification, nothing too crazy, but some of the different things you might want to do. We can also create, similar to our bounding circles, we have envelopes instead of circles in this case. And then we can also perform more spatial analytic functions. So let's take this example. We're going to figure out the overlay. So if those basically intersect or overlap with any two geometries that you want to figure out. So we have our neighborhoods, and we want to see if any of those overlay or which ones do overlay with parks. So, but this would identify as any neighborhoods that do not have a park inside of them. So you can see here that we have our new value all the way at the end. Let's see here. So you can see here that some of these are true and some are false in this case. So to compare this, we can see that there's 2,300 parks. If we have 312 neighborhoods, let's just see which ones overlap there. And you can see the different overlaps or the neighborhoods that are overlapping with those different parks. So nothing too interesting there because pretty much every neighborhood has a park, but just to give you a sense of what that does. You can also go the other way here. And then now we are looking at the overlap of parks versus neighborhoods. So in our first one, we just did neighborhoods versus parks. Now we can go the other direction. Now get into some of the, I guess, lower level functions, which are more kind of, you may or may not use these, especially if you're doing geospatial analysis, but once again, good to know should you ever need to. So this is the offsetting. We're going to just offset or translate this geometry for each point. We're going to move it by a meter of 10 to 10. So these are just slightly shifted up and over, basically. If we wanted to make that much more apparent, we could go 1,000 and 1,000, and we would probably see these shift into somewhere else. Yeah, so now we have these train stations that should be over here are now shifted out into the middle of the bay. So that is showing how those shift and those shifts work there. We can also check if we have valid geometries. We can see we actually have an invalid geometry here. So there's some functions to actually make those valid as well in Geopandas. So you can check validity. You can get the just exterior of the boundaries. So this is very similar to that boundary when if we just wanted the exterior boundary. Sometimes there are interior boundaries. If there's a hole in the geometry, this would exclude those. So you can go those. You can also check out our geometry types. So you can see multi-line strings. And then probably, I guess, one of the more useful ones is getting the latitude and longitude of a different value. So we'll take the schools and we'll get the lat long of each of these using X and Y. So basically the lat and long. You can see here now that we have these values here, and we can kind of compare those to see, yes, these exactly match to our latitude and longitude, which is exactly what we would expect. So nothing too surprising there. Now, the next couple sections will set up for some of the spatial analytics that we want to perform. One more section we'll have after this on spatial joins, which will cover joins in a lot more detail. But this will set up for some of these calculations that we want to perform for our end analysis or our end analytical project. So this is us finding any neighborhoods that wholly contain a park, right? So we're using our basically a double lambda function here, if you want to think of it that way. So neighborhoods geometries, for each neighborhood geometry, we want to figure out the parks that contain a neighborhood, a park that contains or wholly contains the park within the neighborhood. So it's kind of this double lambda function that we're doing there. And we'll see if there are any neighborhoods that do not contain that. And you can see here that there are a few neighborhoods that wholly contain a park. So these are all the neighborhoods that do not contain a park. Now it's strange because some of these neighborhoods are considered parks, as Central Park, so it overlaps at some point with the boundary of Central Park, so it's not considered a full overlap, as well as the airport. Obviously, there are no parks within the boundaries of the airports here. Same with JFK. So you can see some of these are actually neighborhoods that are just complete parks. They're all park. And then we also have some neighborhoods that have no parks within them, such as this one here, which has no park, this city in Staten Island. So those are just basically we're just kind of taking any overlap here with this double lambda function. So we're figuring out for each neighborhood, taking the park and figuring out within that which one contains a park. And then if there's a match of any, we return those there. So in this step, we're going to actually take a look at and figure out if there are any bike paths that cross over the boundary of a park, right? So this would be one that starts outside of a park and ends inside of a park that crosses the boundary. It's not a very commonly used spatial predicate, but I wanted to show at least the number of functions that you use. This is, of course, not an exhaustive list. This is a large number of them, but there are many more that I would not have. This would be a much longer video if that were the case, but this gives you a good sample of that. So you can see I can find any of those that cross. And then here, Central Park is probably the most obvious place to look at this, but you can see that this path starts just slightly outside of that and then crosses into the park, as do these here. So these are ones that start outside a park and go into a park. And you can see all the different bike paths that applies to here. So in this one, we want to find any parks that do not intersect a neighborhood. So we'll see if there are any in that case. And there is one in this case. There's one park that does not. This is a park that is this very small outcropping rock in the middle of where the East River kind of meets the Harlem River. This is the East River here. This is the Harlem River here. So where these two meet, there is this mill rock, which is a park, but of course it is in basically no man's land. There's no neighborhood that exists. There's no people that live there. So this is the only park that is not intersecting or overlapping or have any spatial, relationship with a neighborhood. So that's what's looking at that one. Okay, so now another probably more practical question is, can we find any schools or how many schools fall within 500 meters of a subway entrance? So that's a question you want to ask. So we're going to use our same lambda function structure here just to showcase what that looks like. And you can see here that for each school, we're going to figure out the distance from that geometry. So it's schools.geometry.apply to figure out from the subway's geometry and get any that are within basically 500 or less, 500 and under meters from that location. Now we could, if to write this just as a more proper function, we could go def schools within 500, and we'll pass in the school here. Not to do that, what we would do is you'd basically take this school.distance, this whole function here, and then just return that like this. And then instead of writing all of this stuff here, we could just pass this in as the function here. And that would do the exact same thing. So, oops, I didn't actually define the function. That would help. And we can do that here. We can showcase what that looks like. And then here you can see all the schools that fall within that 500 meters of subway. So you can kind of get a view of where the subways are actually running to and from. Obviously, there is one main line in Staten Island that runs here. So these are the only schools that are close to that train line. Now, in this case, we want to find if there's an overlapping park that sits partially on one neighborhood versus another. So that would basically sit between two neighborhoods. So let's take a look at that. So once again, I have my lambda function. I'm just going to say for each park geometry that overlap a neighborhood geometry, return any results that are there. So we'll return that and we'll see which parks are there. And there are these parks that sit between neighborhoods. There are a few of them that exist. Some of these very long parks, or I guess you could say these are actual parkways, I should say, that between multiple neighborhoods here, as well as some of these larger parks outside of the central Manhattan and things like that. So the last one we'll cover for this section is a symmetrical difference, sort of like kind of a cookie cutter between the two. If these are the parks that are clipping out of the neighborhoods, you can figure out where those kind of areas we want to clip out of those are, and you can find the symmetrical difference between those. So this is one of those things if you need to do some kind of clipping or geometry manipulation. Geopandas has you covered there too. So there's a lot you can do with this. I know there's a lot of in this section to kind of explore all the different relationships. A few things to recap. Number one is that the GeoSeries has a number of functions that you can use to access information about the geometry itself, including measurements and spatial relationships. Those are two of several of them, but you can also pull off of the geometry series or the GeoSeries different predicates such as the latitude or longitude or things like that. You can use functions defined in Python or Lambda functions, along with the pandas apply function to explore spatial relationships between two data sets. We did that several times throughout this section to actually look at things that overlap or fall within a certain distance of. So to do that, we apply a function to the geometry of one data set and then measure or calculate something across that. So once again, similar to this example here, we're looking at the geometry of the park and we're applying this function and finding the neighborhoods that have that overlapping feature between the parks. So that's what we're doing here, is that you can apply those. So that's really the core of these functions. As I mentioned, there are a lot of these. So I didn't even cover, probably half of them here, but you can pick and take a look at all of these. You can figure out it's closed, is empty, is ring, is simple, covers, covered by. There are a lot of functions that actually you can use to compare across all these different geometry series and geometry types. So I'd recommend taking a look at the documentation to get a full picture of what that is. As Like I said, this would be a much longer video if I had to cover all of them, but this at least gives you an example of what they are and, of course, how to use them. So we'll see you in the next section. So open that fifth notebook where we'll take a little bit of a deeper dive into spatial join. Okay, so in this section, we'll take a deeper dive into spatial joins. So a spatial join can either be taking a geometric relationship and retrieving some information about that from to one side of a join, so between two data sets. So how would I define a spatial join? Well, a spatial join takes a spatial relationship between two data sets with geometries, maybe points and polygons, lines and polygons. It really doesn't matter there, and basically allows you to retrieve data from either side of that join based on that spatial relationship being true or false. So that's what a spatial join is. One example of this is for our schools data set. We may want to see which school zone it falls within, and we can label it that way. In addition to that, we can do aggregates and counts of data to actually see the count or the sum of values that fall within a different geometry. So we'll look at both examples here. So as always, we're going to import Geopandas. We're going to set up our files here. This should be pretty easy practice for you now. And this new thing we're going to add in is a spatial index. So we're going to create a spatial index on our neighborhoods. And that will allow us to just have that access to that spatial index. Now, spatial index basically organizes the geometries in a way that makes it more efficient for a spatial join. Just adds a little bit of efficiency for doing that. That's the simplest way to do that. So as you can see, I'm using a new function here. So I want to find the schools within neighborhoods. So that's what we're taking a look at. And it says gpd.sjoin. And you can see here is that it has the different join types. It allows you to figure out the joins between those different data sets, perform a spatial join, and now you can see in this case, it's grocery stores within different communities. That's what they're doing there. So since we applied that spatial index, we have access to that. And what we'll do is we'll do an inner join and using the predicate that falls within. It completely falls within. So we'll run that, and you can see here now that we see for each school, here is our actual neighborhood that falls within. We get all the data from that other side as well. You see East Village, things like that. Now, if we wanted to aggregate those together and get the counts per school and neighborhood, how many schools fall within each neighborhood, we can do that here. So what I'll do is I will break this first function apart. So we have a school count per neighborhood. We're going to create a new data frame. We're using a group by function. So we're grouping that by neighborhood, which is a pandas function, as well as this .ag function. So we're using the school count here. So basically, first we have our schools in our neighborhoods, which is this data frame up here. We'll be applying the group by function to each neighborhood, grouping it by neighborhood, which is what we want. We want to aggregate that and create a new column called school count, right? This will be performed on the right side of the index. So that's what we're doing there. And then we're going to perform a count, you could perform anything, but basically it's saying create a new column called this, use the right side of the data, which is going to be the neighborhoods data set, and then count, and then we're just going to reset the index. So that's step one here. Step two is that we will merge the data frames to preserve the neighborhood geometry, right? This is just going to give us a pure count. So if we look at it, let's run these in different cells so we can actually see what's happening here. And we can see that. And you'll see here is that I have my neighborhood name and then the school count. So like I said, it's creating that school count, doing it on the index right side. If I was to do that on the index left side, I think I would get a much different result. Yeah, that doesn't exist anyway, so forget it. Now, this will actually merge it to the neighborhoods, and I'm going to use this merge function. I'm going to join the schools count by neighborhood dataset join it on the neighborhood and using the left-hand value. And for any that don't have this, I'm just filling it using fill NA, or fill the null values with 0. So in case there are any neighborhoods that don't have a school in them, and there are, consider our neighborhoods like Central Park, there is no school inside of Central Park, even though it's designated as a neighborhood. That is what's happening there. So let's just clean this up really quickly, and I will run that last step here. So we'll merge those in, and then we'll create that into a GeoDataFrame. We have our geometry here and setting that up. And then we can see our school counts by neighborhood. So here's Allerton, Alley Pond, and you can see a few of these actually don't have schools in them. So Alley Pond has no schools. This Williamsburg has 28, Harlem has 45. So you can see all of the numbers of schools. And of course, there are some that we edge cases that we now had accounted for. So this is fairly short section, but this one spatial join function is going to be your way to do a lot of sort of decrease the complexity of some of what you saw in the previous section where you had to do the apply functions or some of the lambda functions. This just makes it a lot easier to do that. So it cleans up that process a little bit in Python to make it very simple under the hood. So it allows you to do that much more efficiently. So it's nice to have this spatial join function, and then also just calling back to the spatial index, making sure you add spatial indices to speed up your joins and make it a little bit faster. Geopandas has really done a lot to improve spatial joins, spatial relationships, things like that. So, and this is just one way to take advantage of all of that they built in. So short, tiny section on spatial joins, but yeah, that's it for this section. And now we will jump into our final. So welcome to the final section of this tutorial where we'll be going through a real world project using some of the data that you've already seen from this tutorial so far to analyze and understand different levels of access to different features within New York City. This will allow you to showcase your skills in Geopandas and actually produce a project that you can use to showcase what you've done. In this project, we'll be doing two different things. We'll be creating a access index that will look at access to different features like schools, parks, and bike paths in New York City using the data sets that we've already been exploring. We'll first do this at the neighborhood level so we can actually see the neighborhoods that have the greatest access. And from there, we'll also be doing this using a spatial index in H3 to understand how this is normalized across space and not just neighborhood boundaries. So if you haven't yet, go ahead and open the sixth notebook in the series. As you can see here, I'm going to start by installing a few other libraries. First one I'm going to do is install scikit-learn, which is basically a very large project that includes things like machine learning and a lot of different other algorithms. But we'll be using it for its normalization functions. So that will allow us to scale our data from 0 to 1 to give it an even score across multiple metrics. Going to install two other libraries, H3 Pandas and H3. This will allow us to use the H3 spatial indexing system in the second part of this tutorial. So go ahead and install those if you haven't already. And then you can see here, we're pulling in our imports here to pull the different pieces that we need here. Now, this should look familiar by this point. We're just adding our data sets here. As you can see, we'll be adding our school points, subway stations, bike paths, neighborhoods, and then parks from all the different data sets. So you can go ahead and run that, and that will pull that in. So in our first analysis, what we're going to do is understand the access to different features in each neighborhood in New York City. So in this case, that's things like the number of schools, the number of subways, the length of bike paths that are within each neighborhood, and then the area of parks or green space within each neighborhood. Now, these are all sort of separate measures. They aren't really tied to one specific thing, but they could just be looking at general livability or access to things like transportation and exercise, fitness, even just access to green space and things like that. So this can give you some metric of access within these neighborhoods. These are also common practices and common analyses that are used in things like equity indices to understand equity and access in different areas from a spatial coverage perspective. So this is actually the basis of a lot of different common, analytics and research in this area. So you can use this as a foundation to go much wider as well if you want to. So what we're going to do is basically just create a simple function that will allow us to analyze these different things in one broad stroke, right? You could run these individually, but what we'll do is basically take this in and pass in our neighborhood geometry here, which is the geometry we want to have access to for each neighborhood. And then we'll do perform the spatial analysis. So as you can see here for the number of schools, we're going to find the number that intersects the neighborhood geometry. So what that allows us to do is get the shape of that, which is basically the count or the number of how many intersect that. Same for subways. And then as you can see here, I'm doing the same thing, but I'm using the length attribute to access the total length of all of those bike paths that intersect a neighborhood and then summing those up. So I'm going to get the total length or the sum, as well as the area here for for the parks. So I'll get the area. And then what I'll do is I'll just return all of these from this function. So the number of schools, subways, bike path length, and park area. And that will give us all the numbers we need to start working with. And then the rest of it will be kind of the normalization steps to make it sort of normalized and comparable across all the different neighborhoods. Now, why do you need to normalize this? Well, if you think about it, if you have, a metric of counts of schools, there may be one neighborhood that has 10 schools and one neighborhood that has one. Whereas a park area, if you may have, tens of thousands of square meters of park area, those two numbers are widely scaled, and if you want them to be weighted evenly, you want to scale them down to a single sort of metric, like a 0 to 1 score, a 0 to 10 score. In this case, we'll use 0 to 1, and that's where we use the scikit-learn min max scaler, which will do that mathematical calculation for us. So one piece I forgot to add in here was actually to transform all of these to set them to the 3857 projection, so we get all of our numeric data back in meters and not in decimal degree units, which would be the 4326 projection. So I just fixed that. We'll go ahead and create the function and then actually run that analysis here. So as you can see here, what we're doing is, since we were returning 4 different columns, we're going to update these 4 columns or create these new columns in our data frame for the neighborhoods. And you can see here that I'm basically just using that function neighborhoods geometry apply, and then the lambda function to pass that over the geometry that I'm pulling in. So what's nice about this structure is that since I'm returning 4 columns here for new data points, I can just add all of those in one clean shot to the neighbor's data frame. So the neighborhoods will add all of these new components to it. And then all I have to do is use that apply function from pandas. So you can see here I'm using neighborhoods.geometry, and across that I'm applying my analyze neighborhoods function, which will run this entire thing out for me. So I don't have to do much extra work. I can just run it like that. We'll go ahead and run that analysis. So what's really nice about this is that basically, since, as you can see, I'm returning 4 values up here, I can actually pass those or create the new values here in that neighborhood's data frame quite easily by just passing all those 4 values. And I'm just going to use my apply function here, neighborhoods.geometry.apply. And I'm going to use the lambda function just to ensure it runs properly. So basically, for each geometry, I'm going to pull in and create a series, which is basically the 4 values that come out of that. Because I'm returning 4 values, I need to use the series and then run the analyze neighborhoods against that. So that's going to run here. And then once that's done, we can take a look at our new data. So I can just see what we get here. And you'll see now that we have for each neighborhood the number of schools, subway stations, or subway entrances, I should say, the length of the bike paths, and then the park area there. So the park area is in the scientific notation, but you can get a sense of that, which is what's there. So now what we'll do is actually normalize our results. So basically, I set up that min-max scaler, which is that 0 to 1 function that comes from scikit-learn. That's the only thing we're using from that, but it's really super simple to use. And then we'll normalize. Here's our 4 columns we want to normalize. And you can see that I define these in a list here. That list will then populate into here. So what this will look like is actually something like this, where I'm recreating those, but it's just a little cleaner. So then I will call the scalar, and I'll use the function fit transform for that to transform those values. And then I will just pass in the columns that I want to normalize. So this will run the normalization, and then I will set it to the new columns here. So once that's run, we can do the same thing. You can just see what those values are again, and you can see now that these are normalized values, right? They're from a 0 to 1. So 1 being the highest, 0 being the lowest on the end of that spectrum. And that will allow us to compare these evenly across each other, which is nice. So to normalize this even further, this is a step you don't necessarily have to do, but it's one I wanted to add in just to show you how you could apply this even further, is actually taking it further and applying and trying to normalize it against the results of your neighborhood areas. Now, the reason we would do this is, for example, in New York City, we know that there's going to be a high density of schools in Manhattan, right? There's just more people, tighter space, density, all those different things. And we want to account for the density of that and normalize against that from the neighboring or the touching geometries of those areas, and understand if there's sort of some factors taking place, and we can compare it against more of the sparsely dense areas in places like Staten Island, or the outer parts of Queens and things like that. So this allows you to do that, and it's just another level of to kind of illustrate what you can do here. So what's going to happen is we'll pass in the neighborhood index or the neighborhood name effectively here. We'll get the current geometry of that value, and then the indices or the names or the indices of the geometries that touch that. So you can see you have neighborhoods, geometry, touches, and then that's our current geometry, which is coming in. So we'll get all of those. And so if it is not empty, right, and if there are at least one touching geometry, it will find those and then just get the touching indices and the columns to normalize and get the average of that. Otherwise, it'll just return basically the values that it already has. So we can go and take a look at that. And once again, we're just using that lambda function to apply that. So this is our columns to normalize, which as you can see here, these are the normalized columns we have. We'll pass the neighborhoods.index and then series. So what that actually looks like is we're just getting the index of each of those. There's 312 in total. So it's just, basically the numbers there, the unique identifiers, if you will. And then what we're applying is our aggregate touching neighborhoods function here, which will give us a new normalization score. So if I look, so I'll actually show that up here so we can kind of compare these side by side. If you look at our values here now, they look slightly different from the number of schools for, let's take a look at, here we go. So if you look at, let's say, this Allerton neighborhood in the Bronx, which is the first one, you can see that the original score here for the schools was actually 0.19, and now it's actually gone down to 0.24 because it's normalizing based on those around it. Similar to park area, which has actually increased, and bike path link, which has decreased. So you can get a sense it kind of helps just add an extra step of normalization to this. We can compare, especially since we have such density in Manhattan and things like that. It's kind of depends on the city you're looking at, but in this case, we know enough about New York City to say that there is that high level density that we want to account for. Okay, so now that we've done that, we can once again renormalize that. We can take a look at our data set here, which all looks good. And then we're going to create a final index score, which is we're just going to add up each of these scores and pull that in. And then what we'll do is we'll just add that data to a simple map in leaf map. As you see here, I added some different arguments. So I'm adding a column of the index score, which is the one I just created. We'll use a quantile scheme and a blues color map to do that. And if we zoom in, we'll see what this looks like. So the darker areas are the ones that would have higher index scores. The lighter areas would have lower index scores. And you can see here is that this did work pretty well because we were able to balance against some of these denser areas in New York. Obviously, these are all kind of, near or touching parks. There's a lot of big parks, obviously Central Park here, as well as some of these other areas out here. But then we have this dense area in Southern Brooklyn and a few other areas as well. So this gives us a complete view of this sort of normalization practice. It allows us to see that there are some of these like outlier areas. So if we look at them, let me just zoom out here so we can see this a little bit better. For example, I think this is Whitestone and Bay Terrace, Bayside in Queens. And you can see here that they have pretty high scores across the board for things like subways and number of this is actually quite low, but park area schools and things like that are quite high. As we compare that to other areas in Manhattan, you can see schools, subways is much higher, park area is quite low. So it gives us this normalized score where you can see that there's differences between all of these. Here we have, very strong access pretty much across the board to schools, subways, bike paths, and things like that. So you get this comparable metric to understand equity and access between these different neighborhoods. And that normalization, that little bit of extra step, just adds one level deeper to do that. So that it kind of, normalizes and gets a little bit of a closer score. But of course, neighborhood boundaries are sort of rigid and defined. We want to maybe understand how that looks like across space a little bit better. So that's what we'll actually do. Before we do that, I just wanted to call this out as I didn't call this out earlier. It's actually how to save a file out of Geopandas. It's actually quite simple. You use this function toFile from Geopandas accessed on a data frame. So if I wanted to save this, you can pass that in. You give it a name of a file and then the driver that you want. So this could be GeoJSON or Shapefile or GeoParquet. GeoParquet has a separate function called toParquet, but nearly any of the file types that we covered that you can import, you can also export to as well. So you can go ahead and run that, and then that will just create this file with that exact name over here. You can see that's my GeoJSON right here, which it's created. So the next step is we want to do this with H3 cells. Now, if you're not familiar with H3 cells, this is known as a global discrete grid. that is set up across the world and goes from level 1 to 15, 15 being quite small, 0 being quite large. So you can actually take a look at this and you can see here this is H3 level 1. So these are, sort of larger at the sizes of countries. And then as we zoom in, you'll see the resolution start to change, but it has this common hexagonal grid across the entire globe. So what we'll do is this is at level 8, which is a little bit big probably for our study. We'll actually go down to level 9, which will, if you see here in Manhattan, gives us a couple of, several blocks, 2, 3, 4 blocks in Manhattan. As you go out to some of the other areas, Queens will be maybe a few more, a few less, depending on what you're looking at. This is Brooklyn, actually, and then Queens over here. So more or less, they'll give you a couple blocks so you can get a much more granular analysis out of this. Okay, so to create our H3 grid, the first thing we need to do is actually reset our projection because H3 works with the 4326 projection. So I'm just going to change the neighborhoods data frame back into the 4326 projection. Now, as you see, we're going to use that resolution level 9, and we're going to use this function h3.polyfill. So apply that to, just as we would another, intersects or something like that, we're applying h3.polyfill and applying that to level 9. And what we can see here is when we open this up, we now have for each of these neighborhoods a list that contains all of the H3 cell IDs. So if we just, for example, to take this one here, if we go over here, I can actually pass that ID in, and you can see that that's this cell right here. And it'll show us the exact cell. So it's just a unique identifier. But what we need to do is take those out of the arrays, or sorry, the lists, and move them into rows as well. So what we'll do is do this here. We're going to do that same sort of process, and we're going to basically explode at, and as you see, it's the same function we have as up above, but we add that argument for explode true, and that will give us all of those in individual rows. So it's repeating each of the rows for each neighborhood here in that case. Now, there's a little bit of kind of funky things we have to do here to get these to work in the way that we want. So this is just kind of some of the unique pieces with the H3 library and the indices and all of that good stuff. So what I'm doing here is basically, let's break this apart line by line, is that I am basically, for this data frame, I'm finding any of the rows that are null, or sorry, that are not null. So this is saying for H3, for the data frame, here. So for that data frame, we just created GDF underscore H3. For the H3 polyfill column here, I'm trying to find any that are null that are false. So that are not null. You can see here that this is all the rows that are not null that actually have a value in them. And then I'm setting the index, instead of having the index be 0, 1, 2, 3, 4, I'm setting the index to that H3 polyfill. So that's what we're doing there. And you can see here that now, instead of that 0, 1, 2, 3, 4 index, I now have the H3 cells. And what I can do from that is actually turn those into boundaries, right? So actual geometries. H3 cell is just right now an ID. Now I'll actually have a geometry that I can work with here. And I just had to reinstall these libraries when I restarted my kernel once. You may have to do that here. But then I'm actually going to open that up and explore the cells. And you can see here that now we have H3 cells covering all of those different areas in New York. We don't have any areas over the water, which is what we want to avoid, and things like that. So we basically have everything that we need here, which is great. So now we want to understand those access metrics. Similar to what we did with the metrics for the neighborhoods, we're going to do the same thing for H3 cells. So what I'm doing is I'm basically creating a buffer 2 times, and I'm going to create one 800-meter buffer and one 1,600-meter buffer. That's roughly in standard, so that roughly translates to about a half a mile and a mile. If you're thinking in the imperial measurement system, it's 800 and 1,600 meters. So what I'm doing here is finding all of the schools that are within 1,600 meters of that cell, all of the subway entrances that are in 1,600 meters of that cell, all of the bike paths or the length of the bike paths that are within that 1,600 meters, and then the area of the parks within the 800 meters. You can play with these numbers if you want to try and adjust them, but what's interesting is that it's actually kind of getting some neighborhood areas, and as you're moving slightly, you're just kind of moving that window around, so you get some of those neighborhood effects that we did with the intersecting neighborhoods. If you remember from the step before, we found the the values of the neighbors, this kind of accomplishes some of that for you. So it's the same sort of thing we're doing here. We're doing that analysis, and then we're applying it and returning these different metrics here. So I did forget one step is that I actually have to set up a new data frame, in this case, to return it to the 3857 projection so I can actually use meters again. So that's what I'll do here. It'll run that analysis for all of the different cells that we have. This is one of the longer steps, I think, in the process because there are about 5,000 different cells that it has to run this for and create the buffers for and do all these different things. But it should be relatively quick. And then you can actually, we'll take a look and see what the results are from there. Okay, so now you can see, just as we did before, we have our data over here for the schools, subways, bike path, and the park area. We're just going to set up a new column called H3 index. So we're going to take the index here, which is the H3 cell, and just add that back into a column just to make things easier. And then now what we're going to do is run the normalization analysis here. So the first thing I want to do is import the H3 library. You've installed it, but you've been using the H3 pandas library, which adds H3 functionality into the GeoDataFrame. So that's how we're able to do these things on the data frame. Now we just want to use those actual numbers there. And then I'll explain what's happening here. So what we're doing here is getting a min-max scaler. So we're scaling these values again for these columns, and we'll process the scaling here. We'll aggregate the neighbors here. So this is a step you can choose to do or not do again, but it just adds another kind of evening out of all the data here. So basically what I'm doing is I'm using this function here called the K ring, right? So this is a K ring value. So if you see each hexagon, let's take this one, for example, you can see that it touches 6 different cells. This first ring is called a K1 ring. It's the one nearest ring. One further out from there adds another set of cells. So we're getting a little bit of a bigger value here too. So that's another value that we're adding in as well. So we're just adding that to 2K rings out to kind of even out the data a little bit more. And that will return those neighboring values. We'll apply that, and then we'll run the normalization again. And then you can save the data out from there as well. So once that runs, we should see our normalized scores again out here. So that looks pretty good. We're going to do the same thing. We're going to calculate our total score, and we're just going to go ahead and add that to the map here. And if we zoom in, we can see now we have this normalized view, which kind of follows some similar patterns, right? But we see some other areas sort of pop up here. We see that area within Staten Island, but you can see it has a much more smooth effect. And you can actually see some of these different things pop up here. What I like about this is that you can see these areas. These are kind of some pockets around train lines in Queens, and then trains moving out towards different areas in Brooklyn. So it gives it a much cleaner view of that as well. You can remove some of these normalization steps just by kind of commenting them out. So if you just wanted to skip the double normalization, what I would do is you can just basically comment out these steps and rerun it. So I'll rerun it on my end, and we'll check what the results look like here. So if we look at this again without some of the normalization, you don't get that smoothness that you would expect from the other one. And so you can kind of see visually why I added that in. You still get the pockets and things like that. So that buffering plus the smoothness adds that little extra kind of, I think smooths out the data a little bit so you can start to see the clusters a little bit clearer and makes it a little bit more visually approachable to someone who might be approaching some data like this for the first time. So that's why I added those steps in there, but just to kind of show you what that looks like without those. So let's go ahead and add those back in here really quickly. And yeah, so you get this little bit of a cleaner effect where you can kind of see these pockets moving throughout the city. I kind of like that you can see these areas that kind of branch out either based on things like parks or subways. You can see there's not a lot of subways out here, but you start to get these subway scores as you move into these darker areas here. And as you move to lighter areas, you start to, I think, lose those subway scores a little bit. But certainly here you also get access, and this is probably, these have high park scores and bike path links. So there's a lot of parks and things like that. So you can start to see how those play out with these different areas depending on what's there and what's not. So similar to here is you have a lot of park area, a lot of bike paths here along the ocean front. And then here, I think there's going to be there's a ton of park area. Basically, there's just a giant park in the middle here, which is kind of throwing off some of these scores. So that kind of brings us to the end of this tutorial. This has been, pretty long, but it's allowed you to understand some of the fundamentals of how GeoPandas works under the hood, how to access and work with some of the different functionality within there, from reading and writing files to understanding how to work with the geometry series and compare that across multiple tables, and then do more advanced things like spatial joins, and then finally bring it all together in the end to perform a very sort of concrete analysis looking at different access metrics within a city, both from a neighborhood level as well as a spatial index level, so you get a nice smoothed out effect. So yeah, I hope you kind of enjoyed this tutorial. Like I said, all these things you can learn in the documentation. So hopefully this gave you kind of a springboard to jump your skills ahead a little bit. But always go back to the documentation, take a look at what's out there, and try to test some of these things on your own to build that out. You can always, consult some of the different AI tools like ChatGPT or Gemini or Anthropic, as they know quite a bit about GeoPandas. So if you have a question or trying to debug your code, certainly lean on those tools, especially if you're just getting started to get going. But hopefully this gave you a good first pass. Now, make sure to, if you've made it this far, to complete the certification. Just head over to moderngis.xyz, or you should see a link here in the description to actually take the test that goes through all the different questions in this tutorial, to just kind of prove that you did it, and then you'll get a free certification that you can share on your LinkedIn to show that, hey, you took this course and you're now a GeoPandas expert. So I hope you enjoyed this. If you did, feel free to share this with your friends. And yeah, thank you.